Hello everyone. This video covers sections 3.3 and 3.4. Now before we go to section 3.3, which is called divided differences, let me refresh your memory on what we have done so far. So in the last two sections, what we have done was to find successive polynomial approximations at a given point. Okay, so at a given x or a given point. For example, we found p1 of x, and then p2 of x, and so forth. So this was linear, quadratic, and so forth. So in 3.1, we use one method, and section 3.2, we use a different method, but essentially we were doing the same thing. In this section, using divided differences, what we're going to do is that we're going to successively generate the polynomials themselves. Remember from the last two sections that Pn of x is the unique polynomial that agrees with f of x at the points x0, x1, all the way to xn, where these are distinct numbers. Okay, so this is the same Pn that we've been using before, but now we're interested in finding the actual polynomial. So the goal of the divided differences is going to be to find the coefficients, because this is technically given. So now notice the following. So if x was equals to x0, then Pn of x0 will give you just a0 plus a1 times 0 and so forth. All of them will be 0. So therefore from here it implies that a0, or the first coefficient, is the same thing as Pn of x0, which will be just f of x0. Then if x was equals to x1, then Pn of x1 will give you now a0 plus a1 times x minus x0, or x1 minus x0, and then the rest will be 0. So therefore a1 will be f of x1 minus f of x0 divided by x1 minus x0. Remember that the polynomial agrees with the function at this specific point, so therefore f of x1 is technically the same thing as p of x1, but we're gonna use everything using the f function. So remember that f and p of x are clearly not the same thing. They just agree at a specific point. So if you have x0, x1, all the way to xn, and if this is f of x, then at these points they will agree, but they're not necessarily the same function. So this will be p of x. Now this will be the notation that we're going to use. This is called the zero difference, and the zero difference is nothing more than the y values. This is the first divided difference. Okay, and so forth. This will be the second, and so forth and so forth. So in general, the divided differences would look like this. Notice that this is also a recursive technique, because this will use the previous values, this will use these previous values, and so forth. So in general, this is what we're interested in. So notice how the bottom are going to be the endpoints, and then on the top, the first part is going to go from here to here, and the second part from here to n minus 1. And there is a typo here, it should be x0. Alright, so therefore the polynomial that we'll get, which is going to be called the Newton's divided differences. Newton actually have something to do with this. It's going to look like this. Remember, this is the first value, and this is the coefficients, and it's going to give you the polynomial. So clearly you can see this is a polynomial of degree n, where the divided differences are given in this table. So you can see how you can form this recursively, and this is very similar to what we did in the last section. So this is the first, the second, and then the third, and so forth. All right, so let's do an example to see how this works. All right, so we're using the same information from the example we did before. Remember here, f of x was equals to 1 over x, and then this will be x0, x1, x2, x3, and this is f of x0. This is f of x1, and so forth. So this will be f of x2. Actually, this should be f of x3. This is the one that is f of x2. All right, so take out your calculator and follow along. Make sure that you stop this and check that this is the right formation. So the first divided difference will be this one, since we already have the 0 divided differences here, which is just the information. So therefore f of x0, this is the formula, so this will be 0.36363 minus 0.5 divided by 2.75 minus 2.0, and this is minus 0.18183. I'm going to use 5 digits because that's what I used in the previous sections, but like I said before, there's nothing special about 5 digits. Then the next first divided difference will be f of x1, x2. So this will be 0.25 minus 0.36363 divided by 4 minus 2.75, and this is minus 0.09090. All right, so let's do the last first divided difference. F of x3 is equals to 0.2, then minus 0.25 divided by 5 minus 4, and this is equals to minus 0.05. All right, so let's move to the second divided differences. So this one is equals to f of x1, 2, which is exactly this value, then minus f of x0, 1, which is this value right here. So therefore, if we plug it in, we will get minus 0.09090 minus 0.18183 divided by 4 minus 2, and this is equals to 0.04547. Again, make sure that you check that you get this. All right, let's go to the next the second divided difference. So then this will be minus 0.05, which is this value right here, and then minus and minus going to give you plus, so it will be 0.090, everything divided by 5 minus 2.75, and this is equals to 0.01818. Alright, so now let's go to the third divided difference, and for this one we need this information, f of x1, x2, x3, which is this value, and then x0, x1, x2, which is this value. So if we plug it in here, we will get a 0.01818 minus 0.04547 divided by 5 minus 2, and this is minus 0.00910. Now, if we wanted to find P2, which remember is the second degree polynomial, then by definition this will be equals to f of x0 plus the sum from k equals to 1 to 2 of the divided differences all the way to xk, and then this will be x minus x0 all the way to x minus x to the k minus 1, which in our case this will be equals to f of x0 plus f of x0 x1 times x minus x0 plus f of x0 x1 x2 times x minus x0 times x minus x1, which will equals to 0.5 plus minus 0.18883 times 3 minus 2 plus 0.04547 times 3 minus 2 times 3 minus 2.75, if here the value for x is equals to 3, which is the same value we used before. Then once you simplify everything, and you should check this is 0.32954, which is exactly the same thing we got in the previous sections. So you should definitely check this. So there is no accident that this is exactly the same value that we got in the previous two sections, because remember this is the polynomial that matches the function at these specific points of x0, x1, and x2. So that's why the answer is the same. Alright, so in a similar way we can find P3 of x, which in our case will be 0.5 minus 0.18883 that's x minus 2 plus 0.04547 times x minus 2 times x minus 2.75, which after this point is just this. So after here is the second degree polynomial. So then it will the third degree, this will be minus 0.00910 times x minus 2 times x minus 2.75, which is x1, and then x minus 4, which is x2. Now if you want to find P3 evaluated at 3, which is the same thing we did here, this is around 0.33181, so you should definitely check this. All you have to do is plug in the value for 3 in here and then simplify, and it should give you this, which you can see this is actually a pretty good approximation, 2.3333. Now for the following example, this is an example that is on the book, so you should do what I did in the previous example to check that these are the values you get. So this is a pretty good practice, so make sure you try this. But if the values are given on a table, which sometimes they are, you just need to know what this means. So for example, this value, okay, remember that's nothing more than f of x0, x1, so this is equals to minus 0.48, 37, 0, 50, 57. And then this value is f of x0, x1, and x2, and that's equals to minus 0.10, 87,339, and so forth. So this one is equals to f of x0, x1, x2, and x3, and that will give you 0.065874. Again, you should check this just using the same formulas and the same method that you used in the previous example. And obviously the last one is f of x0, x1, x2, x3, and x4, and this is equals to 0.001825. So therefore, if you wanted to find a 4-degree polynomial, this will be a 0.7651977, which is f of x0, then minus the first divided difference, which is 48, 37,057, which is this value right here. So we pick this, we're gonna go this way. And then now this will be here x minus x0, which is 1, and then minus 0.1087339, and then it will be x minus x0 minus x1, and then plus 0.65874, but now this will be x minus x0 minus x1 minus x2, and so forth. So this is not the best looking polynomial, but it is what it is. So this is 0.18251, and it will be x minus 1 times x minus 1.3 times x minus 1.6 times x minus 1.9. And if you wanted to find the approximation, which is what the same approximation that the example does in the book, of 1.5, you should check this is around 0.5118200. Now, just kind of a side note for theorem 3.6, if we have a function that has n derivatives and x0 to xn are distinct numbers, then there exists a c such that the n divided difference is equals to the n derivative of the function evaluated like a c divided by n factorial. And notice the similarity with from Taylor series from calculus 2. So calculus 2, the coefficients for Cn were defined to be the n derivative evaluated at some point A or n factorial. So notice how they are essentially the same thing. There is an exercise in the homework that will ask you to show that this is the case, which is not that hard to do, you will see. Now, the last two examples we did for the Newton divided differences. The first example, you check the distance between x0 to x1 to x2 was not equally spaced. For the second example, it was. But therefore, Newton's divided differences doesn't require equally spaced values for x. But if you do, then you can write the formula in a more compact way. And this is what I mean by equally spaced. Let's say the distance between each of them is equals to h. So if equally spaced, so they are equally spaced, then the Newton's divided differences is going to be called forward difference. We also have actually backward difference, which we'll get to in a little bit. And if it is called a forward difference, then we're just going to rewrite this formula in a more compact way. And compact doesn't necessarily mean that it will look nicer, it's just more compact, okay? Using this new notation. So let's look to the connection between what we have before and what we have now. So by definition, the first divided difference, remember, was equals to this. Now, if the distance between x0 and x1 is equals to h, then x1 minus x0 will give you just h. And then we're going to define delta of f of x0 to be equals to f of x1 minus f of x0. By the way, my dog's name is Delta. Not important, but I just wanted to mention it. So therefore, a more compact way of writing the first divided difference. So instead of writing this, we're going to write it this way. Now, if you remember from the last page, the second divided difference by definition was equals to f of x1 x2 minus f of x0 x1 divided by x2 minus x0. Now, since the x values are equally spaced, the distance between x2 and x0 is going to be 2h. So this will be equals to 1 over 2h. So this is equals to 2h. And then times f of x1 x2 minus f of x0 x1. But by definition, the first divided difference is going to be equals to f of x2 minus f of x1 divided by h. and then minus f of x 1 minus f of x 0 divided by h also. Remember that this is x2 minus x1 and this is x1 minus x0, which is just h. So you can take the h out, so this will be equals to 1 over 2h squared. And then by definition, f of x2 minus f of x1, which is this definition, this will just be delta of f of x1, and then this will be delta of f of x0, which by the same definition of delta again, this will be just delta square of f of x0. So that's how we get this formula. And in a similar way, obviously, that's how we will get the k divided difference. So now this is the all notation. So we're gonna rewrite this in a more compact form, and by compact, remember, means using something like this. Here x, remember x is always the value you're trying to approximate. So x0 is gonna be some initial value, which is x0, which we have, plus sh. So we need to figure this out. But h is technically just the distance between the two consecutive x values, like I just said before. So the only value you really have to figure out is the value for s, and this is going to depend on whatever the question is being asked. The question is being asked. So how do we get this value? Remember that x is defined to be this. So therefore x minus xi is going to be just equals to x0 plus sh minus xi, and therefore this will be equals to xh minus xi minus x0, and this will be equals to sh minus ih. Why ih? Because remember the distance between x0 and x1 is just h, so you go all the way to xi, then there is h parts of, I parts of that, and then you can just factor the h, and it will be s minus I. So that's how you get this part. Now, how do we get this formula? Well, let's look to the second term, which is this one. So remember, in the old formula, which is this, in the old formula, this should have been f of x0 x1 times x minus x0, which it will be f of x0 x1, but remember that x is defined to be this, so therefore this will be x0 plus xh minus x0, so the x0s will cancel, so this will give you f of x0 x1 times sh, which is exactly this part right here. So that's how you will get this part. Now to get the second part is done exactly the same way. Remember that you have f of x0 x1 x2, this has to be multiplied by x minus x0 times x minus x1, and if we do the similar substitution, we already know that this part is equals to sh, and then the next one will be x0 plus sh minus x1, so this will be sh times xh minus x1, if you factor the negative sign, minus x0, but remember that this is equals just to h, so it will be sh minus h. You can factor the h, so this will be s of h squared times s minus 1. So hence this will give you this part. So that's how you find those values. So in general, in the new formula or in the new compact form, it will be equals to f of x 0 plus the sum from k equals to 1 to n of s times s minus 1 all the way to s minus k plus 1 times h to the k, and then this will be f of x0, x1 all the way to xn, which, if you remember the combination formula, this is the same thing as f of x0 plus the sum from k equals to 1 to n of s choose k times k factorial h to the k f of x0 xn. Like I say, this is a little more compact. It doesn't mean necessarily that it's friendlier. If for computational purposes, this formula is actually easier than this one. So now recall from some of your previous math classes, the s chooses k is the same thing as s factorial over k factorial s minus k factorial, and this is equals to s times s minus 1 all the way to s minus k plus 1 divided by k factorial. But again, this is usually more useful in practice than to use this one that you will see right now. All right, so let's see how this works in practice. So let's say that you want to find, so let's say that you want to find f of 1.1, which notice that this is going to be approximately equals to p4 or 1.1. Notice that 1.1 is somewhere here. So the reason why this method is called forward is that you're gonna the number you're trying to approximate is gonna come early in the approximation, and you're gonna move forward. You're gonna use all the values to approximate this. Now remember that x was equals to x0 plus sh, and in our case h is equals to 0.3. Why? Because from here to here is 0.3, 0.3, 0.3, 0.3, and the value for x0 obviously is equals to 1.0. So therefore, if you want 1.1, this will be equals to 1 plus s times 0.3, which will give you the value for s to be equals to 1/3 or 0.33 and so forth. Okay? So therefore, if we want to approximate p4 of 1, it's going to be equals to this. So p4 of 1.1 is going to equals to f of x0 plus s of h f of x0 x1 plus s times s minus 1 h square times f of x0 x1 x2 plus and you keep going until the last one, which is going to be s minus 1 times s minus 2 times s minus 3 times h to the 4 times f of x0, x1, x2, x3, and x4. And as you can see, I didn't use a combination. This is easier to follow. Now, notice that we have all the information you need. All you have to do is plug it in. F of x 0, 1 is this value. F of x 0, 1, and 2 is this, and so forth. So we're going to go forward this way. So we plug in the values. We will get this is equals to 0.7651977 plus 1/3 times 0.3 times negative 0.4837057 plus 1/3 times negative 2/3 times 0.3 squared times negative 0.1087339, which is this value right here, and then plus 1/3 times negative 2/3 times negative 5/3 times 0.3 cube times 0.0658784, and then finally plus 1/3 times negative 2/3 times negative 5/3 times negative 8/3. How do we get that? Well, that's from here. If s is 1/3 and you subtract 3, you will get minus 8/3, and then times 0.3 to the 4, and then times 0.0018251. And then once you simplify all of this beautiful thing, you will end up with 0.71964,660. And again, just check this calculation, and that's how you're going to do this forward. Now, the reason why we went forward is because we're trying to approximate 1.1, and 1.1 is here, so we're going to start with the 1.1 early and go forward. Now, if we want to approximate a value here, then we're going to go backwards, okay? And that's going to be called a backward difference. All right, so the backward difference is very similar to the forward, except now you're going to go backwards, and now xn or x is going to be equals to xn instead of x0 plus sh. And notice how we start with n instead of 0 here, and we're gonna go backwards until we get to x1. Here we have a new notation, and the notation is going to be nabla. So now this is called nabla, which is technically a delta backwards, and by definition this is equals to pn minus pn minus 1, and therefore nabla to the k power of pn is going to be equals to nabla of nabla k minus 1 to the pn. So if we do the same thing we did with the forward formula, this is going to become f of xn, and then plus sh f of xn times x minus 1, and then plus s times s plus 1 h squared times f of xn minus 1, and then xn minus 2, and so forth. So the last one is going to be s times s plus 1 all the way to s plus n minus 1 h to the n power times f of xn all the way down to x0. Now we use the compact notation. Is going to be f of xn plus the sum from k equals to 1 to n, negative 1 to the k, and this is now negative sk nabla to the k power of f of xn, which is very similar to the previous formula. So now let's say that now you want to approximate now f of 2.0, okay, which therefore technically we need to find p4 of 2.0. Now we're going to use the same information from the last table, but now we're going to go from the bottom up. All right, so again, like the previous example, you had to figure out what is the value for s, and h is not gonna change. Remember, h is still 0.3, but now the formula for x is x equals to xm plus sh. So therefore 2 is going to be equals to 2.2 plus 0.3 s, which means the value for s is going to be equals to negative 2/3. All right, so therefore you should look to the previous table. The value for p4 of 2.0 is going to be 0.1103623, which, remember, this is f of xn, or the last value, and then it will be minus 2/3 times 0.3 times negative 0.57152110, which is the next value on the list, minus 2/3 times 1/3, which is equals to s times s plus 1. Remember the value for s is negative 2/3, so therefore s plus 1 is going to give you 1/3, and then times 0.3 squared times the value from the table, which is 0.0118183, and so forth. Then will be minus 2/3 times 1/3 times 4/3 times 0.3q, and then the next value on the table, which is 0.0685, and then finally negative 2/3 times 1/3 times 4/3, and then the last one will be 7/3 times 0.3 to the 4th power times the last value, which is 0.0018251. And then when you simplify this beautiful thing, this equals to 0.2238 754 and that's it. Now originally section 3.4 was also going to be included in this video, but it's going to be done in a separate video. Okay? So this is it for 3.3.